last class we had seen two different methods of modeling solids. The first method we had seen was a graph based model or a BREP model, a graph based model, one specific case of which is a BREP model, and the second type of model that we had seen was a CSG model or a constructive solid geometry model. Okay, in the CSG model we said that any solid is built by the help of a set of Boolean operations, and those operations are union, intersection and the difference operation. So you take primitives and perform these Boolean operations on those primitives to get or to construct a solid. For a simple example, if we consider a object like this can be made by a difference operation between this object and this object. Okay, and then an object like this can again be made by a union operation between this object and this object. Okay, and both these, in fact all these three objects are primitives obtained from a single primitive which is a cube. They are transformations of a cube. Okay, so this is how a CSG model is constructed. But one thing that we have to be careful about in using these operations is, let's say if we have a, let's take a simple case, if we have a two-dimensional square, okay, and we take another two-dimensional square which is like this, and we try to find out the intersection. Okay, the intersection of these two, strictly speaking, would be a straight line. Okay, because the set of points between this square and this square, the set of points which are common are just these points. So intersection of these two will just be a straight line over here. Okay, similarly if I want to define a difference of these two, okay, with this set of points minus this set of points, okay, so one line will have to be subtracted. Okay, so these kind of problems can come up. If I just consider this single line, this is not really the result that one would normally like to have in a solid model. Okay, well if we have, let's say, a cube and another cube kept side by side, I'll ideally like to say that the intersection is 0 or intersection is a null set. Okay, so this operation is, let's say if I am doing an intersection over here and I get this result, this is a normal intersection operation. So whenever we are talking of solid models or the CSG model, we don't do a normal Boolean operation, we do what is called a regularized Boolean operation. And a regularized Boolean operation is an operation in which the final result is of the same dimension as the initial result. If you are talking of a two-dimensional object over here, we will not consider cases like this, because this result is one dimensional. Instead of this line, if it was a narrow rectangle, then it is alright, but if it is just a single line, that will be treated as not existing. Okay, so in a regularized Boolean operation, the final result has the same dimension as the initial result. Okay, so normally whenever we are talking of union, intersection and difference operations for a CSG model, we are always talking of a regularized operation, a regularized union, regularized intersection and a regularized difference. Okay, so this is one difference between a normal Boolean operation and the operation that we use in CSG model. This becomes critical when we are writing a program which would carry out this intersection operation. We have to identify cases where such lines are being generated. Okay, or we might have one rectangle like this and another triangle like this, only one point is common. We have to identify such cases and take care of them. Okay. The other thing I mentioned last time, that if I have an object being made like this, these objects are essentially primitives. Okay, they are transformations of a cube. But this object is not a primitive. So if I want to get some properties of this object, I cannot just use the binary expression given over here. Okay, A union B minus C. I cannot use this binary expression. I have to evaluate this expression, get a graph representation of this, or to get the information on the surfaces which constitute this body, and only then I can use this. Again, that process I mentioned was a process of evaluation. Okay, when I have a simple expression like A union B minus C, okay, this expression or this form is referred to as unevaluated or the procedural form. Procedural because it is giving the procedure of how the object is being constructed. Unevaluated because it is giving an expression and not the final representation that would be needed for the solid. Okay, and only when we evaluate this model, that means we get the information of this solid in terms of what are the faces which constitute it and so on. Only then we will call that an evaluated form. Okay, the primitives, like in this case, will be represented using some other modeling technique, let us say BREP. Okay, there can be other modeling techniques that we use for that. Okay, we can, right now we will talk of only the BREP. If you are, let us say, using some other technique here, when we evaluate this model, this solid will also be represented in that technique, not as a BREP normally. Okay, so whatever method we are using for representing these primitives, after evaluation we will try to get this model also in the same representation. Okay, because if we have a model like this, okay, and we want to get some solid properties from this model, it is normally not possible. Okay, for instance, if I just take A union B and I want to find the volume of A union B, okay, volume of A union B, I cannot say that volume of A union B will be equal to volume of A plus volume of B. It will be volume of A plus volume of B minus volume of A intersection B. Okay, so if I have to find the volume of A union B, I have to evaluate A intersection B anyway. Without that, I cannot get the volume of A union B. Okay, so we'll just come back to how to compute the volumes. We'll come back to that in a minute. Let's see one more example of how a solid can be constructed. If you have a solid like this, okay, we can construct this solid by taking this solid and these two cylinders and carrying out the difference. Okay, I'll get these two holes, one hole here and the one hole at the other side. Okay, this solid I can construct by taking this solid, and then these two cylinders, and again carrying out the difference to get this curve, these two curves. Okay, now this cylinder is being written here as pi 2 T9. Okay, I'll write it larger, pi 2 T9. Okay, pi 2 is a primitive and T9 is a transformation which has been given to that primitive. Okay, so pi 2 is being taken as a unit cylinder in this case, and T9 is a transformation which transforms the unit cylinder into this cylinder which has some specific dimension and specific location and so on. Okay. Similarly, when I consider these two cylinders, these are referred to as pi 2 T7. Pi 2 is the same primitive, a unit cylinder, transformed through a transformation T7. That will give us this cylinder, which we will be using in the difference operation with this object to get this, and so on. This object is obtained by taking this object and this disk and carrying out their intersection, so as to get a curve over here. Okay, and this disk is again pi 2 T5, same primitive with a different transformation. Okay, and we will continue further. This object is made by taking this object and its difference with this. And again, this object is made by taking this block and a disk and the union. Okay, this block is written as pi 1 T1. Okay, pi 1 is a primitive which is a cube, unit cube. T1 is a transformation which transformed it into this block. Okay, similarly here I have this as pi 1 T3. Pi 1 is unit cube, T3 is a transformation which converts it into this block. Okay, and pi 2 T4, which is again a unit cylinder transformed into this cylinder. Okay, the point that I want to make out now is that, let's say we have any cube, unit cube. This is a primitive, let's say pi 1 in this case. This I am transforming through some transformation T1, and then I am getting another object, and let's say I have taken another primitive pi 2 which is being transformed through, let's say, T2, and then let's say I am taking some Boolean operation of that, maybe the union. Okay, when I have to evaluate this model, see, this is only a procedural model right now. That means this expression pi 1 T1 union with pi 2 T2, this is only a procedural model right now. When I want to evaluate this, the process of union is going to be very expensive. Okay, well, I mentioned earlier, whenever I have to carry out a Boolean operation, I have to find out the intersection of all surfaces in one with all the surfaces of the other body. Okay, to find out which are the new surfaces which are generated, which are the new lines which are generated, which are the new edges which are generated, and so on. Okay, so union can be a complex operation. Okay, but carrying out this transformation, that is a relatively simple operation. Okay, and these transformations, they do not affect the boundary model. Let's say this solid is represented using either B-rep or some graph based representation. Okay, this transformation is not going to alter this representation. Okay, the transformations are not going to alter the, what do you say, the topology of this object. Okay, the transformations are not going to alter this topology, only the union operation is going to alter the topology. All Boolean operations can alter the intersection, the interaction between the different surfaces. New surfaces can be generated, new edges can be generated, okay, and new vertices can be generated by a Boolean operation. Okay, but that cannot happen by a transformation. Okay, so these transformations are normally relatively simple to use. It's only the Boolean operations which are expensive in terms of evaluation. Okay, if you are talking about a transformation that does not change the topology of the object, only the Boolean operation would do that. Okay, transformations would change the properties of this solid. Okay, properties meaning if I want to compute the volume of this object, a transformation can change the volume of this object. Okay, because I can change this cube into a maybe a block or a rod or anything. So the volume of this object can get altered. Okay, but the topology or the interaction between the surfaces, that will not get altered. Okay. Now now let's see if I want to compute the volume of an object. How can we compute the volume of an object represented in this manner? Okay. For instance, as I said, if I have A union B, I want to find the volume of this. This will be volume of A plus volume of B and minus volume of A intersection B. Okay. In this case, if I can ensure that A intersection B is equal to 0, okay, that is equal to a null set, then the volume of A intersection B will always be 0. Okay, so there are modeling techniques which ensure that A intersection B will always be 0. Okay, the intersection of all solids will always be 0 in that case. We will see some of those modeling techniques. Okay, so in that case we can easily use this operation or this method of finding out the volumes, because A and B will be primitives or will be derived from primitives. So the volume of the objects can be easily computed. Okay, and we know that the intersection will always be 0, so we will always ignore this term. But if that does not happen, then we have to use the boundary representation of the solid. Okay, if we have any arbitrary solid, let us say this solid, and we have its boundary representation, we have the equations of all its faces and the interaction with the other faces and so on. We can use that representation to get the volume of the solid. How we can do that? See, the volume of a solid is the volume integral of dV. Okay, similarly, if you let us say instead of a volume, if you want to find out some other property, maybe a moment of inertia about a particular axis or something like that, then that will be equal to integral of f times dV. The f is some function of x, y and z. Okay, so we are interested in evaluating this integral, and this is, we want to find out the volume integral. Okay, this is equal to some property of the solid. Okay, now for evaluating this volume integral, we know the volume in terms of its bounding surfaces. So we will try to break down this volume into a surface integral. Okay, for breaking down a volume into the surface integral, we will use what is called the Gauss's theorem. Integral of del dot P with dV is equal to the closed surface integral of P dot n with dA. Okay, where the del operator is del by del x, del by del y, del by del z. Okay, and P is any field. Okay, P is a vector field in space in 3 dimensions. Okay, so let us say if I want to find out the volume, what I want to do is I want to ensure that del dot P should be equal to 1. Okay, so for ensuring this, we will take P to be equal to x 0 0. Okay, that means it will be x I plus 0 j plus 0 k. Okay. If I take P to be this, but del dot P will be equal to 1, because I will take the dot with this operator, and we will get del by del x of x plus the other two terms is 0, which is equal to 1. Okay, so del dot P will be equal to 1 in that case. Or instead of x 0 0, I can also take P to be equal to 0 y 0. Okay, or I can take it to be 0 0 z. Okay, if I take del dot P to be equal to 1, that means let us say I take P to be x 0 0, and I want to find out this integral, That means surface integral of P dot n with dA. Okay, so this will become a surface integral of x 0 0 dot with n and integral over all surfaces. Okay, this means that if I have any boundary or any solid at each of the surfaces, I can find out the direction of the unit normal vector. Okay, and if I know n for this surface, I can get an expression for this integral. Okay, since I know n, I can take its dot product with x 0 0 and then integrate it over this surface. Okay, because I know the equation of this surface, I know the details of this surface. Okay, and this I can repeat for all the surfaces which are defined in this solid. And the details of the surfaces are known because we have a boundary representation model. Okay, so we can evaluate this integral and this will be equal to the volume. Yeah. See, let's say I have two solids A and B. Okay, I have done the union and now I have a solid A union B. I know the boundary representation model for A, I know it for B. Okay, but if I have to find the volume of A union B, I have to evaluate A union B first. That means I have to get the B-rep model for A union B. Okay, that means let's say if I have one block like this and a second block, let's say which is something like this. Okay, let's say initially it is longer. Once I do the union, I get this block with a handle on top. Okay, I'll have to get the B-rep model for this complete solid, which will be this top surface with a cut in between, these vertical surfaces only up to this point, and so on. Okay, just by looking at the B-rep of A and B-rep of B, I cannot find the volume of A union B. I have to get the B-rep of A union B. Okay, that is why in order to find the volume or in order to compute any properties of A union B, I have to evaluate A union B first. Okay, unless I evaluate this model, it is not going to be possible for me to compute the volume. Okay, for most of the operations, even if I want to, let's say, display this, okay, it is normally not possible to do it unless you evaluate the model. Okay, normally there are techniques which do it, but let's not go into that at the moment. Okay, so evaluation has to be done. Only once the evaluation is done, you have a complete B-rep model of A union B. Only then you can apply this method. Okay, and this function that we take P, okay, the field that we are choosing P, that will control what property we are trying to evaluate. Okay, let's say if we want to find out the moment of inertia. Okay, the moment of inertia, we can let's say if I want to find out the moment of inertia about the z I z z, which is equal to integral of x squared plus y squared dv. Okay, so we want that del dot p should be equal to x squared plus y squared. Okay, so what should be the p that we take? We want del dot p should be equal to x squared plus y squared. Again, x cube by 3 plus y squared x times I, okay, plus 0j plus 0k. Okay, or alternatively I can take x cube by 3I plus y cube by 3j. Okay, so del by del x of this will give me x square, del by del y of this will give me y square. Okay, I can take this to be the expression for p. So del dot p will be equal to x square plus y square. Okay, and then again I can find out the integral of p dot n. I'll take a dot product of this with all the normal vectors of the surfaces and compute surface integral. Okay, that way I will be able to evaluate the moment differential. Okay, let's say if I am taking p to be equal to this, my del dot p is equal to del by del x of x cube by 3 plus del by del y of y cube by 3, which is equal to x squared plus y squared. Okay, so whether I take this p or whether I take this p, evaluating the integral del dot p dv will still give me the same moment of inertia I z. Okay, the choice of this function p or this field p is not unique. In what? In this? You have to differentiate this term with respect to x. Okay, so this will give you y square, this will give you x square. You have to differentiate this with respect to y and this with respect to z. Okay, so you will still get x square plus y square. Okay, so the choice of p is not unique. You can have different sets of p still giving us the same moment of inertia. Okay, depending on the moment of inertia we need, or depending on the property that we need, we'll choose a different value for p and carry out this integral. Carry out this surface integral. Okay. Now the next thing that we can see is that, let's say if I am taking a cube, a unit cube as a primitive, I can transform the unit cube and get even a plate and even a thin vertical rod. Okay, this is simply by an operation of scaling. Okay, but quite often we can have complex objects. Okay, for instance, we take a angle. We have an angle like this, which has, let's say, certain radius of curvature here, certain radius here, certain radius here, certain thickness here, some thickness here, certain height over here, okay, and certain length over here. Okay. Now, let's say in some application we are using angles of different sizes in different places. Every time I want to make a model of this angle, it can become quite a complex process. Okay, making an angle like this would mean that I'll first take a plate, horizontal or vertical plate. I'll take the union, then I'll take a fillet over here. Okay, then maybe I'll take another fillet here, and so on. Okay, plus this angle can also have a draft over here. That will complicate matters even further. Every time I have to make an angle, one would normally not like to go through a sequence of steps like that. Okay, so what is often done is we make primitives which are complex objects like this. Okay, and these primitives will have certain parameters. Let's say this is A, I call this B, I call this, let's say, T1, this is T2, let's say this is R1, R2, let's say this is R3. Okay, so we define these parameters, and this primitive is defined by the help of these parameters A, B, T1, T2, R1, R2 and R3. Okay, so all these parameters together will be defining a primitive like this. Okay, so whenever we use this primitive in any application, we'll have to specify these parameters. Okay, so this is what is referred to as a parameterized primitive. Parameterized or generic primitives. Okay, in addition to specifying a transformation, which will convert this unit cube into either a plate or a rod. Let's say this is a transformation T1, this is a transformation T2. In addition to that, for the case of parameterized primitives, we also have to specify the values of these parameters. Okay, so in a particular situation, I might have a solid A, which is actually, let's say I have some primitive pi1, which I am instantiating through a set of parameters P. A is equal to P of pi1, let's say. Pi1 with a set of values attached to it, which are P. Okay, and this A is referred to as an instance of pi1. This is a generic primitive. When I give some set of values to it, this is referred to as an instance of this generic primitive. Okay, and let's say I can have a number of such parameterized primitives. And then I can perform Boolean operations on them. Okay, so this process of instantiating a parameterized primitive gives us, in some sense, a family of primitives which have the same topology, which have the same adjacent surfaces. Surface adjacencies are the same. Even if I take a different value of T2 or T1, my surface interaction is not going to change. Okay, so this process of parameterization is similar to the process of transformation, in the sense that it does not alter the boundary model. It does not alter the topology of the object. Okay, so this process is relatively inexpensive, and after taking a instance of this primitive, then we can carry out a Boolean operation. This Boolean operation cannot be performed unless we take an instance of this primitive. Okay, the Boolean operation can only be performed if we take an instance, because unless we give some values to these parameters, we don't know the exact sizes of these surfaces and locations and so on. Okay, so typically if we are talking of a CSG model using parametric primitives, in that case we will have a process of parameterization. Then again, of course, there can be a transformation also. This parameterized primitive can be transformed and then used in a Boolean operation. Okay, because just a single transformation cannot help us to get the different sizes of the angles. Okay, but if I give it a non-uniform scaling in a two direction, the different parameters will not change proportionally. Okay, so we have a notion of what is referred to as parametric or generic primitives, which help us give us, in some sense, a family of primitives, and in a particular application we give values to these parameters through a process of what is referred to as instantiation. Okay, and then we have an instance of these generic primitive being used in any particular application. Okay, and if you want to find out, let's say, any property of this this primitive, either the volume or the moment of inertia, the volume of this primitive, that we can compute by the help of some formula which can be known to us. Okay, for finding out the volume of this, I need not carry out a complex integration. Okay, the volume will be some function of these parameters, the p's. Okay, even the moment of inertia will be some function of these parameters p. Okay, and these properties, the formula for these volume and the moment of inertia, etc., these can be stored along with the model of these primitives, so that one doesn't have to carry out a complex integration to find out the volume of these primitives. Okay, and as I mentioned, the process of this instantiation that does not offer that does not alter the boundary model for these primitives, that does not alter the topology, and the BREP model will remain unchanged. Okay, so when I am evaluating this union, the BREP model for pi 1 will be the same as that for A, and will be the same after transformation T1. Okay, so the expensive process will still be the union. Okay. Any questions on this? Same topology. Okay, the adjacency relationship between the different surfaces will remain unchanged. Okay. Any question on this? Okay. Now let's see the other method that I mentioned, that where the intersection of the different solids is always 0. Okay, and that is, let's say one method is okay, this is a method what is referred to as cell decomposition, and this is a set of methods all of which come under this category. Okay, what is generally done is, if you have any solid, you will decompose them, you will decompose that solid into a different set of parts. Okay, so let's say if I have a cylinder like this, okay, with maybe a handle over here. Okay, let's take a realistic thing. It's a hollow thing, and it's got a disc at the bottom also. Okay, this solid, I can represent that by one simple hollow cylinder, its union with a disc, and its union with this handle. Okay, so what I am effectively doing is, I am taking a solid like this and decomposing it into 3 different parts. Each of these parts can now be represented relatively easily. Okay, and I'll say this solid is the union of these 3 parts. Okay, in this method, the intersection between any of these solids will always be 0. We ensure that there is no intersection between these. We are just decomposing this this solid into a set of smaller or simpler solids. Okay, then each of these solids can again be further decomposed if need be. Okay, but we will not have any intersection between 2 primitives. Okay, so for creating a solid like this, we are in effect starting from the initial solid and then decomposing it. Yeah. What do you mean by approximate? I'm coming to that. The method in which we do that also. The cell decomposition is a set of generic methods. This is one way of decomposing it. Okay, we will talk of other methods in which any complex object will be broken down into a set of small cubes. Okay, I will be coming to that shortly. Okay, so this method is referred to as cell decomposition, or these kinds of methods are referred to as cell decomposition methods. The advantage that we have is that since there is no intersection, the properties can be computed very easily. Okay, but there are times when this kind of method can become slightly complex in creating an object. Okay, because you have to know the final object, what its shape will be before you decide what will be the primitives. Another type of cell decomposition method is what is referred to as spatial occupancy enumeration. We just consider two-dimensional example to start with. For instance, if we have let's say this is a square and my object is let's say something like this. Okay, that means the surface that I want to represent is just this surface. The outer square that I have drawn, that is just the limits of this surface. Okay. What we can do is we can divide this square, we can divide the limits of this surface into a set of very small squares. You can divide it into an array of squares. Okay. And then for each of these squares, you can say whether the surface exists there or it does not exist. Okay, so we'll get an array of zeros and ones. So this complete this complete area will be divided into an array, let's say x in this direction and y in this direction. And if I say an array A of xy, such that A of ij will tell us whether the surface exists at location ij or not. Okay, if ij is this particular square, okay, let's say if ij is this square, okay, this square is ij. Aij will be equal to 0 if it is outside the surface, it will be equal to 1 if it is inside the surface. The surface is defined in this case by this boundary. Okay. We obviously have a problem if my square is partly inside and partly outside. Okay, if it is something like this. So in that case what we will do is we can either decide as to what is the resolution that we want. We do not want to consider squares which are smaller than a per given size. Okay, or we can subdivide this further into a smaller array. Okay.
Smaller number of small size squares edges. We did not have this unmeshed node.
Okay, we'll see that also. But right now, what I'm saying is, we just want to store it as a simple array. Okay, then that will not be possible. Okay, because if it is a uniform array, you like your squares to be uniform. Okay, so if you want to have a non-uniform size of the square, that will obviously save some space for the area which is not there or the area which is totally inside. So there you can have a large size and then you can have a small size at the boundary. Okay, but then you have to keep track of the size of every cell. Okay, we'll see methods for doing that also. Okay, so if you're just keeping a uniform array, and for every cell we say it is either a 0 or a 1, depending on whether it is outside or inside. In that case, we like to have a uniform size of the cells. Okay, and then we can enumerate each cell being either a 0 or a 1, starting from one corner and going up to the other end. The disadvantage is obviously that if you have a very if you want to have a very high resolution, you end up using a very large amount of space. Okay, because we want the same size being used all the way through. Okay, the space required will become very large. And then if you are going into, if you want to extend this onto 3 dimensions, it can become even more complex. The space required will be really very large for a 3-dimensional object. Okay, so in order to take care of that, we use a method which is normally referred to as either a quad tree in 2 dimensions or an octree in 3 dimensions. Okay. What we'll do is in the next class we'll see what is a quad tree and what is a norm tree and how they are used for representing solids. Okay, we'll see that in the next class. Any question on what I've covered today, especially the last part, spatial occupancy and emanation? Okay, in that case the next class we'll go on to quad tree.